Greetings everyone. We're about to begin Unit 9 about oscillations. So in the last lecture we discussed a simple pendulum and what the period of oscillation for that pendulum would be. And we derived this expression which depended upon the length of the pendulum and the gravitational acceleration rate, but did not depend upon the mass of the pendulum. And so we said that depending on what planet you're on, this time period is going to be different depending on what the gravitational acceleration rate is on that planet. So this was actually done by the Apollo astronauts. When they went to the moon, they had a pendulum swinging, and you can see that if you click on this video, you'll see that the period of oscillation seems rather slow compared to what we would expect on Earth. So I brought this idea of a pendulum up to you to discuss gravity, but also as a segue into thinking about periodic motion. In fact, as a pendulum swings to and fro, it is an example of some sort of periodic motion. And if we take, say, a conveyor belt underneath a pendulum and stick a pen on its end, you would see that as the conveyor belt moves and the pen traces out the motion, it produces essentially a sine wave. So there's some sort of periodic sinusoidal oscillation that is occurring with a simple pendulum. And we want to delve into this deeper in order to start to understand these types of periodic motion. So let's take an example of that simple pendulum once again and model it as a massless string with a weight on the end. The forces involved on this pendulum then, on the bob of the pendulum, are the tension force and the weight force, producing this gravitational acceleration rate g, which has a component in the centripetal direction and in the tangential direction. So that if we think about what's going on with the tangential acceleration, this tangential acceleration is equal to g tangential, okay, which as we see here is g sine theta. Now we know that tangential acceleration in general from our rotational kinematics equation should equal the radius times alpha, the angular acceleration rate. And so in this example, the radius is the same as L, the length of the pendulum. And we can rewrite this angular acceleration rate as the second time derivative of the angular position. When we do this, and then we plug in what g tangential actually is, we arrive at a second order differential equation for theta. If we approximate that this angle is small, then sine of theta equals approximately theta, and you have this second order differential equation here, d squared theta dt squared equals minus g over L times theta. The solution to this second order differential equation is indeed a sinusoidal function, as you see it here, where in the argument of the cosine, this omega is the square root of g over L that appeared here in the differential equation. Okay, so we can check and make sure that this agrees with what we have done last time. There's a relationship between this angular frequency and the period of oscillation, whereby 2 pi over the angular frequency should be equal to the period of oscillation. So if we plug in what g over L, square root of g over L is into this equation, we get back the same expression that we had before for the period of a simple pendulum. So all of this checks out. And again, we found that the period is independent of the mass. So this simple pendulum is one example of what we would call simple harmonic motion. So what is simple harmonic motion? Simple harmonic motion is any sort of periodic motion that occurs whenever a force that's acting on the object is proportional to the position about some equilibrium point. So that is to say that we could be talking about angular or linear displacement about that position. And objects or systems that obey this sort of simple harmonic motion we generally refer to as simple harmonic oscillators. So we've just explored the simple pendulum, which is a simple harmonic oscillator, and the displacement is really sort of an angular displacement about the equilibrium position. But we could also talk about simple harmonic systems where there's linear displacement about some equilibrium position. And what should come to mind when we think about a linear displacement from equilibrium and a force that's proportional to that displacement? A good example would be Hooke's law. And indeed, a mass on a spring can form a different kind of simple harmonic oscillator. So if we take Newton's second law and we set it equal to Hooke's law, so that we're assuming that there are no other forces present on this mass spring system other than Hooke's law, so we're kind of ignoring friction and so on. And then we re-express ma as m times the second time derivative of position, then we arrive at a very similar second order differential equation to the one we saw before. Instead of thetas and g's and l's, we have x's and k's and m's, but the form of the equation is essentially the same. And as such, it's going to have basically the same solution. It's just that now our omega is square root of k over m. So we can make a generalization here about simple harmonic oscillators and say that basically the solution to these type of differential equations is going to have this form where we have some amplitude times cosine of this argument here, and inside that argument the omega, the angular frequency, is just going to depend upon what kind of a simple harmonic oscillator you're talking about. For a mass on the spring, it's square root of k over m. For the simple pendulum we explored earlier, it's square root of g over L. There's also something called a physical pendulum, which we will talk about in the next lecture, and that angular frequency has a mass in the numerator, but actually it also has a moment of inertia in the denominator, so that these masses end up canceling, and it's really just a distribution of the mass that will end up mattering for this physical pendulum. Okay, so at this point I want to relay some basic definitions so that we can better understand this equation of motion. So in this equation of motion we see a number of different variables. What do they all mean? So this A stands for the amplitude, which is the maximum displacement away from the equilibrium. Phi is a phase angle if there's any sort of non-zero angle at which the motion was started at time equal to 0 and it was at some different point in the cycle, for example. Capital T and F are not directly mentioned in this equation. However, they are derivable from this omega, the angular frequency. The angular frequency is related to the linear frequency by this factor of 2 pi, and then the linear frequency is 1 over the period, so that we get back this relationship I mentioned earlier, that the angular frequency is 2 pi over the period. Okay, so with all of those definitions out of the way, let's take a look at this graph here where we have displacement as a function of time for a simple harmonic oscillator. Let's take it to be a mass on a spring. And we want to take this equation of motion for the position of the mass on the spring and express it for this particular mass spring system. So we want to write down some equation, in other words, for x of t. In order to do so, we need to know what A and omega are. If we take this phi, there's no phase angle involved, to be 0, then we just need A and omega. So we can get this information by looking at the graph. A is the amplitude, so that is the maximum displacement away from equilibrium, which we can see if equilibrium is 0, this amplitude ought to be 3 meters. The angular frequency we can figure out from this graph because this is a displacement versus time graph. So when this has gone through an entire period, then we can look and see how much time that took and plug that in to figure out what the angular frequency is. And you can see that the entire period takes 6 seconds to get from this peak to this peak. And so this means that the angular frequency in this example is 2 pi over 6, which simplifies to pi over 3. And therefore, our expression for this simple harmonic oscillator is, as you see here, 3 cosine pi over 3 times t. So that gives us an equation of motion for the position, but what if we would like to know something about the velocity? So we can derive an expression for the velocity if we recall that velocity is equal to the time derivative of the position. So really, this is just an exercise in performing a derivative to this expression here. When we do that, the derivative of cosine is negative sine, and we also bring out an omega out front. So that all corresponds to choice D for our expression for the velocity as a function of time. So with this expression, let's take a look at another object in a mass spring system and plot its velocity as a function of time. And what we want to know here is, what will my amplitude for the position be? So bear in mind that if this is our expression for velocity, then A is no longer the amplitude. We actually need the amplitude. To find the amplitude, we need the entire A times omega. Nevertheless, we can figure out what the amplitude is from this graph, and if we know something about the angular frequency, then we can figure out what just A by itself is. So some of the parameters of this particular simple harmonic oscillator are going to be the same as our previous one. In particular, the time period is 6 seconds to go from one point in time to the next identical point in time in the cycle. And so that amounts to an angular frequency, as before, of pi over 3 seconds. So what does that mean? That means that my amplitude is going to be this entire thing, but that amplitude is equal to A times omega. The entire amplitude, as before, is 3, but look at your units this time. This is 3 meters per second. So 3 meters per second equals A times omega. And that means that A by itself, if I plug in what omega is going to be 9 over pi, which is 2.86 meters. So that if I wanted to write the expression here for position as a function of time, I would need 9 over pi here for my amplitude times cosine of pi over 3 times t. Okay, so let's go a bit further then, and if we have position as a function of time and velocity as a function of time, what about acceleration? Maybe we would like an equation for that as well. Well, acceleration is really just the second time derivative of your position, or the first time derivative of your velocity. So this is again just an exercise in taking a derivative. We may as well just take one more derivative of the expression that we had found on the previous slide for velocity. And when we do that, the derivative of sine is going to be cosine. We keep this minus sign then, and we bring out another omega. And so that all of that corresponds in these choices to choice D. Okay, so let's go back to the original mass spring system that we were looking at on the first page, where we derived the position as a function of time. And now that we have expressions for both velocity and acceleration in addition to position, let's look at how those things play out in a position versus time graph, velocity versus time graph, and acceleration versus time graph all at the same time, and compare the results. So if this is our position equation, 3 cosine of pi over 3 times t, that amounts to this graph here. If I take the derivative of this, I get this graph here. And if I take the derivative of that, I get the expression for acceleration, which is plotted here. So let's see what's happening at different time periods with the position, velocity, and acceleration, and check to see that this makes sense. So first of all, what's happening when the displacement is at its maximum or minimum? So when we are at a maximum or a minimum, that actually corresponds, for example, at time equal to 0, to a velocity equal to 0. And an acceleration that is also maximal but in the other direction. So a maximum in position corresponds to a minimum in acceleration, and a minimum in position corresponds to a maximum in acceleration. So what's happening here is that this is where the mass in your mass spring system is the most displaced from the equilibrium point. And so at that point in time, the object is instantaneously at rest. It's reached its maximum point, it's come to a stop, and it's about to turn back and go the other direction. So that's why the velocity is equal to 0. And because it's the furthest away from the equilibrium position and the force is proportional to that displacement, then the force is going to be maximum at that point. And therefore, since force equals mass times acceleration, the acceleration will be the amount of it, or the magnitude of it, will be maximum. Why is it in the opposite sense? Well, because it is a restoring force. It wishes to bring the object back to the equilibrium. So if F is at its maximum, the A is at its most negative. So X is at its most positive, A is at its most negative, to bring it back towards the equilibrium position. Now, another point in time we could look at is what happens when the position is equal to 0. So right here, when it crosses over 0, what's going on with the velocity and the acceleration at that point? Well, that corresponds to a maximum value for velocity. And for acceleration, that amounts to a 0. So how does this make sense? Well, when the x is equal to 0, it is not displaced from the equilibrium at all. And so the force being proportional to displacement means that there cannot be a force at that point, and thus there's no acceleration at that point. However, if you think about the motion leading up to this, the object was coming from some extreme displacement and being accelerated and moving faster and faster, so that it's already gained all of this momentum and the velocity is now at its greatest magnitude at that point. So all of this checks out with what we would expect for some sort of simple harmonic motion. So let's do an example where we have a cart attached to a spring on a mostly friction-free air track. Obviously, we can't completely eliminate friction, but for the most part, we can approximate this as only having the force, the spring force, at work on this mass spring system. And so we want to know, based on the graph here of velocity versus time, which direction was the cart displaced before it was released. In the past, students have struggled to answer this, so let me just tell you what the answer is, and then we'll talk about why that makes sense. So the choice that's correct here is choice B, that it was originally displaced to the right. It had to have been displaced to the right. How do I know that? Let's go through the motions. If the right is positive x and the left is negative x, then if I've displaced it to the right, I've pulled it over this way, what's going to happen when I let go? When I let go, the force is going to seek to bring it back to the equilibrium position, so it will start moving in the negative direction, right? The negative x direction. So that checks out with time equal to 0, where I have a negative velocity. Moreover, as it continues to move closer to the equilibrium point, remember that it's gaining speed because there's a force acting on it. So a little bit later, it's going to be a little bit faster, and that also checks out. It's becoming more greater in magnitude in the negative direction. But eventually, it will overshoot that equilibrium point and go off to some maximum displacement in the negative direction, in which case it's going to, in the process, start to slow down, right? So as the force starts working on it, it will start to slow down, and then eventually it will come to a stop at that most extreme point of displacement, and then it will start to turn around and go in the positive direction. All of these values correspond to velocity now in the positive direction, right? And then this is even later, and then even later it becomes more positive, and so on. So see if this makes sense. It should all check out with what we decided made sense on the previous slide. Okay, so let's do another example where we're going to model a failing shock system and the oscillation that results as a mass spring system. So perhaps the shock absorbers are no good anymore on this car, and a person of a fairly large mass climbs in and displaces the spring. We're essentially considering this person to be compressing the spring this distance. Okay, and then as soon as the person hits a bump and the spring gets released, this produces an oscillating motion. You may be familiar with this as a school child if you sat in the back of the bus and hit a bump, and then there was some oscillation up and down as a result. So if we want to model this as a mass spring system using the equations of motion that we've just discussed, one of the things we're going to want to know is something about the oscillation period. So remember that for a mass spring system, the angular frequency is going to be equal to square root of k over m, which is 2 pi over the period. So the period then is going to be 2 pi times the inverse of this angular frequency. And so that corresponds here to choice C. We also are going to need to know something about this spring constant K. And so when we apply Hooke's law, what are we counting as the force that resulted in this displacement? Well, if the car was in equilibrium, it was in the equilibrium position before the person got in, then the mass of the car doesn't displace the spring, nor does the sum of the two. It's the added mass of the person that displaces the spring, and so this corresponds to choice A. So now with those two things that we've realized, we have enough information in the problem statement to actually compute what the spring constant is and what the period of oscillation is. So the spring constant, based upon the mass of the person times g divided by the displacement, is going to give us this value here. The period of oscillation then is going to be 1.07 seconds. Okay, and so then in addition to that, we are going to have to know, if we want to write out this equation, a cosine omega t, we're going to need to know what A is. Well, A is the amplitude. It is the maximum displacement that we're going to have. That's occurring when we originally compressed the spring here, so A is going to be equal to D. So these three ingredients are sufficient now for us to figure out then what we need to turn this equation into. So I'm going to first start by plugging in for the amplitude this displacement here of 0.028 meters, and then I'm going to multiply that times cosine of omega t, right? So omega t is going to be this same as 2 pi times the square root of k over m. I'm sorry, just k over m. So we have then the k spring constant, which is 38,500 divided by m. Now, why is this? This whole mass is relevant, not just the person's mass, because once the thing is on oscillation, it is the entire mass that then is oscillating. And then we're multiplying that by time. To simplify that then, the equation turns out to be the following. 5.9 times time. Okay, so we've successfully modeled this bad shock absorber and as the mass spring system that you see here with this equation of motion. I want to give you one more example in this lecture, and then we will do some additional examples in the following lecture. So the last example for this lecture is the torsional pendulum. In the torsional pendulum, the restoring force is given by the torque. I'm not going to bother deriving this, but you can think about this as a torsional equivalent to Hooke's law, where we have a constant times a displacement. This constant is the torsional constant, and the displacement this time is in the angular sense, so we have theta. Okay, using Newton's second law for rotation that we've used before, if this is the only torque present, then this torque is going to equal I times alpha. So this restoring force being equal to I times alpha, where alpha is the second derivative of the angular position, gives us another equation that has the same sort of second order differential equation form as what we've seen before. And in fact, this then is going to be our omega squared, and so therefore the period of oscillation being 2 pi over omega will be equal to 2 pi times the square root of I over kappa. Okay, so that's a general equation for any sort of torsional pendulum. And so you can see that it depends upon the moment of inertia of what is attached to this pendulum here. So let's take a tangible example and say that we can model this as a disk, as a simple disk. If you recall from our merry-go-round problems, that disk then has a moment of inertia of 1/2 mr squared. You can also look this up, of course, in a table. And so the period of oscillation then for this specific type of moment of inertia, where we have 1/2 mr squared, when we plug that in for the moment of inertia, we get 2 pi times square root of mr squared over 2 kappa. Okay. So you can see then that the period of oscillation will depend strongly on R, right? So the larger we make this disk, the longer the period will be. Of course, there's also a torsional constant in here in the mass that we have to worry about as well. But let's make the situation just a little bit more complex. And let's say that instead of just a simple disk, where the period of oscillation would be what we had on the previous slide, where we had 2 pi times the square root of mr squared over 2 kappa. Let's say instead that we have placed some sort of mass on the edge of this disk here. And now we want to know how the period is going to change. Well, you see that the period is going to depend on the moment of inertia, the square root of the moment of inertia, so that if I increase this moment of inertia, I'm going to increase the period. What happens when I add the mass to the edge of this disk? Well, the moment of inertia now is what I had before, the moment of inertia of a disk, plus I've got mr squared related to this mass. This is just like when we had the child that was jumping onto the merry-go-round. So now this becomes 3/2 mr squared, which is greater than what I had before. So I'm going to expect the period will increase in this case. If I had an actual classroom to share with you, I would show you a demo about this. I'd encourage you to check out a YouTube video. You can probably Google this. Otherwise, we can just take the numbers at face value and see that that will increase the period. If you want to know specifically by how much it will increase the period, you plug in this moment of inertia and you see that it will increase the period by a factor of a square root of 3. Next time we'll discuss a physical pendulum and some other examples related to simple harmonic motion.